что непонятно?
Не, по логике все понятно, почему непонятно. Просто, ну, придется, ну, я так смотрю на
Я
домашний.
чувствую, что тебе тяжело сейчас идет. Вот
Не тяжело, просто довольно много времени придется потратить на то, чтобы разобраться с функциями, погуглить, как это работает. Ну, это окей. То есть сказать, что логика или математика непонятны, не готов. Единственное, что придется много чего пересмотреть. Вот у нас был пример выше, где мы транспонировали матрицы, перемножали одно с другим там, и так далее. Вот этим придется чуть поковыряться. А в остальном, ну, в принципе,
понятно.
ну,
Видишь, и эту лекцию про Deep Learning я считаю как отдельный 6-часовой блок. И сейчас я пытаюсь ее рассказать за там, пару часов, чтобы понятна была остальная часть про регуляризацию. И поэтому оно немножечко выглядит скомканно, потому что оно есть немножко скомканно.
не, где-то в чем-то мы это уже там группой, ну, там, не сказать, что прям в первый раз видим, да, но сейчас действительно это звучит лучше на самом деле, чем
Меня
то, как...
утешаешь.
Не, это на самом деле так. Ну, я бы не сказал, что здесь что-то, ну, тут еще можно спросить, как бы, ребят, я бы не сказал, что в логике где-то есть какие-то или пробелы, или непонятно, или что-то еще. Нет,
Хорошо.
такого нет.
Ну, просто я согласна с тем, когда ты читала это летом в УКУ, это было типа более логично, подробно, пошагово, и поэтому, наверное, была большая картина в этом всем.
Да, потому что в УКУ я читал это вот с самого нуля про Deep Learning, а здесь я решил пойти все-таки в регуляризацию, не в Deep Learning, потому что я же надеялся, что ваш был курс по neural networks, типа не буду же я рассказывать все то же самое. Ну, плюс просто было, ну, если бы я начал Deep Learning рассказывать, то получается, что я бы не успел ничего из Advanced, я просто бы рассказал то же самое, что вам уже рассказывали, только другими словами. Это был сложный выбор, надо сказать. Я не уверен, что я счастлив полностью, что я сделал именно этот выбор. Может, лучше все-таки надо было вам рассказать unsupervised, а потом перейти в Deep Learning. Все было бы плавно и более понятно. Но да.
Ну, сложно сказать, какой выбор правильный, но вот, опять же, мое личное мнение, предыдущие 2 дня отлично, логично легли. Ну, я же говорю, что здесь мне придется чуть больше времени потратить на то, чтобы...
Ну, видишь, а здесь, получается, мы перепрыгнули 3 лекции. Мы такие, ну, давай в регуляризацию, значит. А там в регуляризации уже и Deep Learning известен, и все эти вещи, типа, все понятно. Потому что между регуляризацией и supervised learning идет, значит, сначала unsupervised, там PCA, все вот эти variants, вся эта штука. Потом идет кластеринг, потом deep learning, сначала feed-forward, потом backpropagation, потом идет конволюционные сетки, как они составляются, с чего они состоят, что такое эпохи, как training losses считаются и так далее и тому подобное. А потом только начинается регуляризация, и получается, что мы немножко, ну, да, в общем, так как получается.
Дима, тут еще в этом примере, знаешь, что из моего опыта confusing, то, что тут у нас 2 аутпута. Обычно, если мы это запускаем как регрессия, или там еще добавим один hidden layer, то у нас один output, который там и дает probability класс zero. А тут 2 аутпута. И вот некоторые на этом подвисают, зачем нам тут 2 аутпута, если у нас класс 0 или класс 1. Вот. И тут... Ну,
типа можно, да, я согласен с этим,
Это вот это вот немножко это, потому что оно, когда ты потом экстендишь, что это to multi-класс, это makes sense. Но когда именно 2 класса, то это как бы confusing.
Да,
Когда
согласен.
10 классов, то тогда уже да.
Я согласен, да. Если бы, в принципе, если думать об этом, что это как подготовка к мультикласс классификации, когда ты делаешь. И это тоже не совсем так, потому что там используется softmax, тогда у тебя probabilities одна из другой вычитается. То есть, а здесь это больше такой концептуальный пример, просто что вот есть некая архитектура, вот так она работает, и мол, не вашего ребята ума дело, мол, почему она так составлена, как она составлена, это немножко так бесит, да, на некоторых этапах это бесит. Okay, shall we switch back to English? Kenneth, I'm not sure, are you around? So yeah, we have a few more minutes before the start. I just wanted to say that this architecture is completely it's an arbitrary architecture. So it's not really some kind of useful or important or fixed or standard. It's just a very small architecture just to illustrate how the bias is and how the feed forward works. Yeah, and I do recognize that this part about having two answers instead of one answer for a class, this is a confusing part. But let's just stick around with this example and see how far it will lead us. All right, so where we go. Let's wait for another minute, and then hopefully Simon could join, and then we can get back to this. Please ask questions or make your comments about this part that we had. As I was just describing, this deep learning lecture is actually a 6-hour module. So that if it feels a bit messy, that's because it's not really, it wasn't really discussed from start to till the end. It's just parts and pieces of this lecture. And I guess right now we are just getting through here because I felt that it feels like you're having gaps in understanding of backpropagation and deep learning in general. So we decided to catch up this part. Okay, Simona's back. Now that we have calculated the errors for each class, we can calculate the total error. Right, the total error is just the sum of these two classes errors, right? Just we take one error and the other error, we sum them up, and this is our total error for this specific example, right? So the error of this network, which is a randomly initialized, arbitrary constructed. So these are arbitrary neurons. I mean, I could have had 3, 4, 5 neurons here or more or less, but this is just to this is an example architecture that I just made up. Okay, and we calculate the error for this point, and the error is 0.307, right? So this is the error for this point. Now, what happens now is that we need to reduce the total error. We need to make changes into neural network. We are unhappy with neural network. We think that the neural network can do better. And we are unhappy in that sense that we want the neural network to make changes into weights so that the error will drop. Okay. How we do it? The only thing we can change in this architecture right now are the weights. Okay. These are the weights, and we can change them. We can either increase or decrease these weights. Ladies and gentlemen, this is very important. So this is all we have. These are all tools. These are all possibilities that we have. We can only change these weights. There is nothing else we can do. In real life, of course, this is not completely true. We can change the architecture. We can change the activation functions. But if we fix the architecture, the architecture is fixed. We don't change the architecture. Then the only thing we can change is the weights. Okay. Let's consider a very specific weight. Let's consider an example of weight W5 and try to answer a question: how does W5 influences the total error? Right. So this is a major question that we will be focusing on throughout this. I don't know, an hour. Perhaps this would take us somewhere about an hour. So the question is: how does W5 changes the total error? How can we, what is the most naive way to check that?
Change it and look.
Change and look, exactly. What if we change it and we just look at it? We can change it randomly and see what happens to total error, right? What if we increase it? For example, we increase the weight by 0.05 and the total error increased. We decrease it and the total error decreases, right? What if we keep decreasing? If we decrease it more, the total error decreases. What if we decrease even more, then the total error decreases even more, right? So that is just a very simple way to check what happens, how the W5 influences the error, right? This is the positive relationship. So this is the relationship that we looked at yesterday when we checked out the linear regression. So this is the relationship in which one thing increases and the other one increases as well, right? So we increase W5, the error increases. We decrease W5, the error decreases. Okay, does this make sense?
Yep.
Everybody? Any questions? Okay. So what happens is that, well, we had to, there is a downside of this approach. So the downside of this approach of randomly changing a weight and seeing what happens is that we need to recalculate the entire chain, right? When we change W5, we need to recalculate the score, the class score. Then we had to recalculate the error for the first neuron, and then we have to recalculate the total error. Oleg, why is it a problem?
The problem that we have this multivariation, yeah, that it means that we need to fix other coefficients on one hand, and then it's.
Yeah, that's true. These could be influenced by other coefficients, and if we start tweaking other coefficients, this could change. But what is a more straightforward problem with recalculating all this stuff? Simon, what's the other problem? Time. Yeah, it takes time. That's a problem. I mean, we need to do a lot of computation. We need to compute a lot of things. And in this case, in this very particular case, there are not too many to recompute. But in the case of a larger network, this is gonna take ages, right? If for each of the small changes, we will recalculate the entire path, this will take us ages. All right, so yeah, and there is another problem that we have not one weight, but we have a lot of weights. So if we start tweaking all these weights, it's gonna be intractable, right? It's gonna be a nightmare. It's gonna be infeasible. So if we start tweaking all these weights, it's gonna take a lot of time. Plus, we don't know if changing one weight wouldn't really change the layout, the surface of the cost function for the other weight. Meaning that if we saw that by decreasing W5, the total error was decreasing, but what if now we change something in weight 3 or 4? Would that also change the way how W5 influences the total error? We don't know, right? So this approach may not work. So we want to find something, we want to find a way to update weights so that they decrease the total error, and in the best way possible, so that it's the most computable, the most effective, and so on and so forth. So what happens is that we actually want to compute the gradient, right? What is the gradient? Igor, what is the gradient? We have 1, 2, 3, 4, 3 Igors right now in the call. Can one of these Igors tell me what's the gradient?
A multi-Igor problem.
Multi-Igor problem. Kenneth, what is the gradient?
The gradient is the edge of the function.
So the gradient is
like
the vector that's
sliding the edge of the curve of the function.
Yeah, so it's a vector that shows the direction of what increase or decrease of the function. Increase of the function, exactly. So the gradient shows the direction of the greatest increase of the function. So this would be the gradient, the total error with respect to weights. Okay, that's how we denote the gradient. So we take the gradient of error with respect to weights. And we are not interested, well, there is one small caveat here. We are not interested in increase of the function, right, Oleg? Because the function is the error, right? The total error. So what we are interested in is an opposite direction. We are interested in decrease of the function, right? So that's why we need to take the negative gradient, right? And we can do it for W5. That's all fine. But how about, all the other weights that exist up there? Well, we have tons of weights. We have millions potentially weights. Does it still make sense in the high dimensional neural network environment? And it turns out that gradients can still be computed effectively in a backpropagation algorithm. So the backpropagation algorithm is about computing weights so this updates the gradient of the weights with respect to, the gradient of the error with respect to all the weights effectively. This is all about the backpropagation algorithm. So what the backpropagation algorithm actually does. We want to let's focus on this W5. So the question is how W5 influences the total error. That's the question we want to find the answer to. How do we change the W5 so the total error decreases? What we do, we compute a partial derivative of the total error with respect to W5. This is the most math-heavy part of the lecture. So what we need to do, we need to compute a stepwise function, right? So we do compute first how the total error changes with respect to the error of the first neuron. How this total error is dependent on this error. Okay, that's the first thing that we need to compute. Then we take this part, the denominator, and we put it into numerator, and we find out how this error of the first neuron depends on the class score. How the class score influences the error of the first neuron. How this value influences this value. What if this value changes, how this value changes? Okay?
Mm-hmm.
Does it make sense, everybody?
Yep.
Oleg, Simon?
Yes, yes.
Igor? If you're there? Hopefully you are. Lena, does it make sense? Okay. It does. Okay.
It does.
Mm-hmm. Now, can somebody predict what happens now? What is the next part of this equation? Oleg, what's the next part of this equation? Oh, this was unexpected, right? Started asking questions.
Some derivative, but of what? Again,
Simon,
output.
can you help? Can you help?
Not now.
Not now. Thank you very much, but no, thank you. No, I'm happy. That's okay.
Output with respect to the function or output with respect to W5?
That's very good. So how the output of the neuron depends on what? So the next part of this equation is having the output in the numerator, but what is in denominator?
So I guess it's the function, the sigmoid function.
Sigmoid function, but
because there's W5 and there's also whatever the other one is too, right? It's not, W5 isn't the only.
Yeah, but okay. So if we have the output, we also have input, right? So we can also calculate how the input influences the output, right? So we can ask a question: how the output is influenced by the input of the neuron? Then this is what you're saying by sigmoid. So this is the sigmoid. This is over sigmoid here, derivative over sigmoidal function. And then the last one, Simon, still. What's the last part of this equation? What is it that we want to ask the last thing?
The function itself.
What is the function itself? Tell me the ratio here. What is divided by what?
Take into account the previous steps. First, I think this derivative of IN.
So input of the neuron 1
yes.
is influenced by what? What is the main question that we are trying to answer here?
W5.
By W5, okay.
Okay, so this is how the input of this neuron is influenced by W5, okay?
Mm-hmm, mm-hmm.
Okay. So here you go. We originally was interested in how the total error is influenced by W5, right? And this is the equation. So this is a partial derivative, the product of partial derivatives. We start with the total error, Then we go into the error on the first neuron. Then we ask ourselves, how the output of the first neuron is influencing the error on the first neuron. Then we ask ourselves how the input of the first neuron influences the output of the first neuron. And then finally, how W5 influences the input of the first neuron. And if we would, the chain goes like this, how the total error is influenced by W5. This is the entire chain.
So mathematically, we could just cancel out all those middle terms. So what's the utility of?
No, we don't cancel out all the middle terms. This is so the derivatives, the partial derivatives. You cannot really just say this is output in the upper part, this is output in the lower part. Just cancel them out, and everything is happy. No, it's not really like that. But let's just see how this works. So let me remind you that the total error of the entire network is the error on the first neuron plus the error on the second neuron. Now the question, the question for millions and millions of dollars. Not even what is, but what if we try to find the derivative with respect to E01? So we take a derivative of this guy by E01. What is the derivative? There is a very simple answer to this.
This is E01.
No. So we take a derivative of this expression by E01. So it's, imagine like this.
It's 1, excuse me, it's 1.
Yeah. Oleg, do you see why it is 1?
So because for derivative O1, E02 is a constant, yeah?
E02 is a constant, and E01 is x
it's
by which you take a derivative, right?
Yeah, and then it's 1, yeah. So
exactly
1 plus 0, yeah.
Yeah, 1 plus 0, but we're just interested in 1. All right, so this part equals to 1. All right, this part of the equation equals to 1. Now, what about the next part? So this part. So if you remember, then the error of the first neuron is this 1/2 the true value, which is true label 0, minus output of the first neuron squared.
So just true
now
output then.
Wait. Lena, what is the derivative of this function with respect to out01? So think about this like this. This is a constant. You can think of it as y, and this is x. And you take in derivative of 1/2 y minus x squared with respect to x. You can, you're absolutely welcome to write it down. 1/2 y minus x squared, and this is derivative over x. Can anybody tell me, okay, Kenneth, I think you know what the answer is. Can everybody, besides Kenneth, tell me what's the answer?
I think this is truth minus out.
So what happens first is that we take a derivative of this, of the thing under the squared. We treat it as x, by which we take a derivative. So we take a square, we reduce it to 2, coefficient 2 multiplied by 1/2 is x, which is truth minus output. And then we also take a derivative of this complex function, meaning that we take a derivative of what the hell is under in the bracket. So it's -1 that is in the
minus bracket. minus 1, yeah.
Yeah, so this is what happens, right? This is the basically taking derivatives. This is what we used to study in high school, but I understand that it's completely not trivial. Many years after the high school, it's completely not trivial. But this is what happens. This is what you get when you take this derivative.
1985.
Sorry?
1985 was when I was doing this.
1985. Okay, I wasn't even born there. I was doing it, I think, in 1998 or something like this. Maybe no, a bit later. I don't know when they started teaching us derivatives at the high school. I don't know. But anyway, it's 0.751. That's the derivative of this result. And now the sigmoidal. Sigmoidal is the most complicated because I wouldn't be able to come up with the response to this one, but there is a very handy shortcut. So instead of taking the sigmoidal of x here, we take we use this equation here. So we treat it like this. So output O1 times 1 minus output O1, and then this is the derivative. This is already the derivative. So this is a shortcut for taking a derivative of this function with respect to x. So people came up with the shortcut. So instead of taking derivative by hand, they came up with this shortcut. And it's 0.186, okay? Now it's the most complicated one, the most complicated. Can you take a derivative of this statement with respect to W5? Lena, please, can you take a derivative of that statement with respect to W5? Oleg, what's the derivative of that statement with respect to W5?
Was the first value output H1, yeah?
Yeah, because this one will go away. We take a derivative by that value, and the rest are constants. Okay, so the only thing that's left is this output H1, which is, by the way, 0.5933, which Simeon helped us to calculate on the first place. If you remember correctly, this was what Simeon told us, that this is 0.59, and this is the derivative. Finally, we can multiply all these things together, and we get 0.082. Now, if value of the gradient is positive, then if we increase the value of W5, the total error will, what happens to the total error? If the gradient is positive and we will increase the W5, the total error will
increase.
Increase, exactly. It will increase. So we need to subtract. And we subtract this very specific value. This gradient is what we need to subtract from W5 in order to decrease the value of the total error by 1 unit, whatever that unit is. So that's the law. You subtract the value of the gradient in order to decrease the total error by 1 unit. But here's the problem. We usually don't subtract the gradient like this. We don't take the entire value of the gradient and we don't really subtract it from W5. We actually, most of the time, we use some learning rate. We use some coefficient. So here's the problem. Here's the curve of the error with respect to W5. And this is a minimum where we want to get. This is where we want to get. And this is what the step of the gradient might look like, right? So we need to go this way in order to decrease the error. But if we make a too high step, too large step, we will overjump the minimum. We will overjump the minimum, right? We will decrease the error, but we will still be not in the minimum. So instead of making a full step, which is this value, we make a part of this step. Let's say half of this step, or even less than half of this step, in order to make sure that we are not overjumping the minimum of the function. Does this make sense, ladies and gentlemen?
Yeah, so do we just use this calculation to figure out the direction of the jumps, basically, is all we care about? And then we set the step based on some other small amount.
Coefficient, yeah. We set the step with some other coefficient. We can call it there are many names for it, but usually it's called either step size or learning rate. So these are called step size or learning rate. And we make it small. Normally it's even smaller than 0.5, depending on number of weights. More weights you have, smaller the learning rate, because more weights you will be updating every time. So usually very large networks have very small learning rates. And if you have too large learning rate, you can still see this escalation of the learning curves. This is one of the good ways to understand that basically your learning rate is too high. Yeah, so this is how you update the weight. You updated the weight W5. The original weight value was, Igor, what was the original weight W5? What was the original value?
0.4, as I remember.
Yeah, it was.
I don't remember.
Yeah, this here the original value here.
Yeah.
So we subtract half of the gradient and we get this new value, which is 0.359 in this case. And then we recompute all the other stuff. And the cool thing about this gradient is that we don't have to calculate it only with respect to W5. We can calculate it with respect to all the weights in the network in a very nicely parallelized fashion. So this is going to be very easy to calculate weights for the entire network using just one gradient backpropagation algorithm. And if we do this backpropagation algorithm many times, then we decrease the error to something very, very, very small. So we update the weights with respect to the gradient many times, and then we get into very, very small error.
You're saying it's easy just because computers are good at calculating that.
Yeah.
It's a linear equation or whatever, sort of.
Yeah, so, it's easy because the computers are good at this. We know how to compute these gradients very fast. You saw that these are basically multiplications, and these are, in this sense, these are matrix multiplications that I told you that we are very good at calculating quite fast. So that's why computers are quite fast.
So actually, backpropagation algorithm, this is an optimization algorithm for multi-coefficient configuration
models. Yeah, it doesn't have to be a neural network. You can do backpropagation algorithm for linear regression, for example. So you can do all the same stuff for the linear regression, and I think that's what in fact is done by scikit-learn package. They do backpropagation for the linear regression. More questions about this?
A question about the learning step. Tell me if I'm not correct, but as far as I understand, if we calculate the gradient descent step by step, we will not miss the minimum of the function. If you do it step by step, after every step, we will not miss. So not necessary to divide it by 2.
The problem is the gradient only cares about the direction, and it gives you this kind of, it gives you a value by which you need to, well, you need to increase first, but when you take a negative of that value, then by which you need to decrease your weight in order to decrease the total error by 1 unit. But then the problem is that there are many weights. And this function is not like I showed you here. It doesn't have to be this very simple function. It could be a very multidimensional hills that you basically, if you make a step, very large step in one direction, you may end up in the peak of the mountain. And that's why, and then when you try to make another step towards another direction, you basically will be jumping on the mountain tops and never actually converging to the minimum. That's why people usually take a coefficient and they take a smaller step instead of larger step. You will be jumping around minima if you make steps of the backpropagation algorithm, but you may be basically, you may never be able to actually step inside the valley, step inside.
If the first jump is big enough to jump over the valley. If the first step doesn't jump over the valley, then you'll be fine and you'll get there because it's decreasing.
Yeah, you can get stuck on the plateau. You can stuck on a flat surface that doesn't have any changes in the loss function. You can end up in the series of hills that are very close together, but the gap between them is so small that you may never be able to step inside of this gap. So that's why you usually.
But if the function is convex, then we can use the. We should not use we can avoid this coefficient, correct?
Again, I think even if it's convex, I think you can. I think without coefficient, you may still never converge. I think you need the coefficient in order to make sure that you converge. I think even if you have a convex function, you need to have a coefficient. And moreover, we use also learning weight schedulers. So sometimes we start with the bigger learning rates in order to jump to the place with the
Get close.
smallest. Yeah, and then we start to slowly decrease the learning rate so that you wouldn't able to jump off the nice place. Okay, so that is also something that people use. But I'm not an expert, so Simon, I wouldn't trust myself in here. I would definitely go and check it out just to make sure that whatever I'm saying makes sense. Okay, never trust me with my words. Never trust anybody.
Okay.
Don't trust even Roman Koch. He's a very important person, but don't trust him.
But this every time we run every time we run back propagation, we recalculate the gradient, correct?
Yeah, every time we run the back propagation, and now you know when we run the back propagation. Lena, when do we run back propagation with respect to batches and all that kind of chemistry of the training? So do we run back propagation for each point, or do we run back propagation for a batch?
For batch.
For batch, and if you run it for batch, then what is it that you use? So what is the error that you're using? Are you using like a sum of errors of individual points? Are you using like a product of individual errors, or are you using something else? Anybody help? Igor?
Average error.
Average was.
Yeah, it was average. Yeah, so no worries, no pressure, Lena. No pressure. Don't worry about stuff. Okay. Right. So that makes should make sense. Now we can go back to the regularization lecture, and this one has the last piece, which is so we discussed explicit regularization methods like dropout, L1, L2 regularizations. And now we have, oh, sorry, I lost my, okay, I'm not showing the slides. Okay, now I'm showing the slides. So now we have been discussing this part of the regularization methods, but now we're left with another one, which is called implicit regularization methods. So while explicit regularization methods, they kind of put additional constraints on top of the model. The implicit regularization methods, they give enough space. They give more space for a model to express itself. So let's see what I mean by give enough space to express itself. Remember the data set. This is the same data set that we have seen for the batch, back propagation and batches and all that kind of stuff. So now we remove the test set. We create a validation set. We have batches. We have batch 1, 2, and 3. We have a model. So the first batch, so when we have one iteration, one epoch, we have training loss, which is the average of the batch, right? We also produce a validation loss. Then we take a second batch, second epoch. We take the same batches. We produce another lot. Of course, you remember that we have done a backpropagation algorithm, so our model is different now. And now we take a next series of batches, again, the same data, and we produce a new loss, new training loss. And here we produce another validation loss. And we take a third epoch, we go into third epoch. Again, the backpropagation, we change the model. We go into epoch number 3. We use the same data, all the same batches to produce another training loss estimate and another validation loss estimate, okay? The problem could be that my validation loss may start growing or may stop decreasing at the best and may start growing. Why do you think my validation loss may start growing? Igor, why do you think my validation loss may start doing this weird stuff?
Overfitting.
Yeah, but what exactly is happening? What's your interpretation? Why does it start growing?
Validation loss is growing. Well, we didn't took right learning steps, maybe.
Could be possible, but maybe something else. Simon, what do you think? What is happening here?
Training model training model just remembers all the available points.
Yeah, that's what I was trying to say. I was trying to say that the problem is that every epoch we fed the same training examples, training images, and there were not that many of them. So we basically, the network learned to memorize training examples like a poem. It knows that the first one comes as a cat, the second one comes as a cat, the third one is a dog, the fourth one is a cat, and it learned this kind of stuff. It now knows that, all right, so these are my training examples, and it doesn't know anything about my validation images, so it tries to do the same stuff with validation images. My validation images are not part of my training data, so it gets lost. It doesn't really know what is happening. It's getting worse, right? So the overfitting gets worse when we have a limited set of data. So what can be done? We had too few images. What can be done is that, by the way, what do you think can be done? Elena, what can be done? If we have too few images, what is the most naive way to increase the number of images? Or maybe Igor, what do you guys think?
The first that comes to mind is we have to reshuffle the images. Then we can just copy them as many as...
Okay, yeah, that makes sense. So let's just we could just copy them, right? So yeah,
we can go on the street and make another quick photos of cats and dogs.
That's what I was thinking.
You know what, guys? I had listened to a talk by Fei Li. You probably don't know who is Fei Li, right? But she is head of the computer vision group at Stanford, and she has, so what she was telling us was that when they started working on when they worked on image processing and computer vision, what they were doing basically, they were going up there in the streets and actually making pictures for their own data sets. And this is what what Fei Li is most famous for. What is she famous for?
Never heard of her. Never heard of her.
Okay, Alexander, do you know what Fei Li is famous for? Let me tease Alexander. He is on the call,
nope.
So I can't just. No, you don't know. So she is the one that came up with the ImageNet dataset and the competition. So she was the one behind the ImageNet competition and dataset. So she was the one to organize this huge collection of images. So for you guys who don't know what is ImageNet, it's a large data set. It's 1.2 million images of cats, dogs, and whatever other stuff that was there on internet. That was it was categorized into 1,000 categories. So there are 1,000 categories in this data set. 1.2 million images, 1,000 categories. It was a tremendous crowd-sourced effort by volunteers from the entire world. People were just sitting at the computer and they were labeling the images. They were saying, this is the image of the cat, and this is the image of the baseball hat, and this is the image of the mirror, and that kind of stuff, right? So this was a large undertaking. This was a large initiative. And then they made this huge data set, which allowed people to compete. They were developing better models. And eventually, this is the competition, the ImageNet competition. This is eventually the place where the first convolutional network has been proposed. This is where deep learning revolution started. In 2015, when the first deep convolutional network by Alex Krzyzewski and others were proposed, and that one has improved the current state of the art on this data set by 10%. So previously, every year, people were making like 2% gap or something like this. They were making better algorithms. But then the guy with convolutional network showed up and he made it, he cut the difference in 10%, which was extraordinary. And that one started the deep learning revolution. So that's how the all this stuff happened. But anyway, so Igor, what you were saying is makes complete sense. I had just another idea here is that if this is 100% data set and you're saying that test percent is my 20% of my data set, test set is my 20%, then I can, and validation set is 20%, then I can just basically decrease reduce the set sizes, right? I can say that let's have test set 10%, and my validation set will let's keep it like this, and then the remaining would be my training data. So this is one legit way to increase your training set size, but there might be a problem with getting a very small test set. Can you guys name it? What is the problem with having a small test set?
All cat.
For example, you can have all the images cat, right? Or you can have a very unstable performances. So if this all the images are cat, then you basically will not be having an accurate representation of the model performance. So you wouldn't know how exactly the model is performing. So you need to be very careful when you reduce the size of the test and validation sets. Like this, for example, 5% and 5%. These are not good sizes for validation and test set. They should be big enough to represent the data. They should be large enough to be representative. Yeah. So what else can be done? And we asked Igor, and he said, you know, guys, you're just wasting time. Why wouldn't you just copy paste images like that? Just take image and copy paste it. What's the problem with this? Simon, what do you think? What's the problem with this?
So if you do not change pictures, we will have this few same pictures in one data set. Seems will not positively affect our training.
Yeah, just like running more epochs of the same data.
Exactly. It's just like running more epochs of the same data. So it wouldn't really change things much. But what can be done to these images? What can be done to these images? Yeah, we could do all sorts of, stuff to these images. So, yeah, I was just saying here that it wouldn't change much, but instead of naively copying, we can transform images a little bit. So let's see how can we transform images a little bit. Let's take a look. So this is how I transformed images, and let's just take a look at every transformation that I have done here. How you can transform them. You can, for example, vertically and horizontally flip the images, right? So these are flipping the images. You can turn images. This one is a bit tricky because sometimes it doesn't make much sense. For example, if you're working with classifying images of cars, then it's highly unlikely that you will have a car that is standing on its top, right? So you should be very careful about using any one of these, because you may not have this in the data set, so they may not be useful. Sometimes you may go for changing the saturation levels. You may either make it very high saturation level or you make it very gray. You can increase the contrast. You can increase or lower the contrast. And you can do all of this. You can do all of this together. You can do, you can flip, you can turn, you can increase or decrease the contrast on the same image, right? So these are called augmentations. These are called data augmentations. You can find a lot of these types of augmentations on the libraries. There are many libraries for image augmentations. For example, one of my favorites is imk-aug, which is image augmentation library. Image augmentations are very popular because basically you can come up with zillions of ways to augment images. For example, one of the recent papers, this is one of the recent papers for image augmentation. Here is the original image. And these are the different augmentation strategies. These are different augmentation strategies. For example, one of the strategies is take an image of the cat and just overlay with the image of the dog and have a different transparency levels. So you have let's say 40% of the cat and 60% of the dog, right? Then when you predict a class for this image, you're now saying this is a cat with 40% probability and this is a dog with 60% probability. This would be a correct label for this image, right? Another strategy is to cut out some space from the image. So you make your network work harder by guessing what is on the image without some part of the image. You can, instead of just cutting out the image, you can paste you can paste some other image in the gap, right? And then you can do all sorts of creative stuff like attentive cut mix, where you not just cut some part of the image, but you cut out the important part of the image, so that the network now has way harder times figuring out what was that image. Okay. So this is the recent paper. I have it as a bonus exercise. If you want to try it, please go ahead and try it out.
And do all those work?
Yeah, these all work with a different efficiency, but and for different problems. But for the classification, it has been shown to work. It has been shown to improve the performance.
So Mixup has like a ratio answer. Does it would cut mix have a ratio answer, and attentive cut mix a ratio answer as well?
Yeah. These two also have the same kind of prediction ratio. This is called label smoothing. When you say that I don't predict just 1 or 0, but I also predict the shade between these. Okay.
So, and then a human being assigns that, or that's algorithmically assigned?
Oh, you just decide on how much you cut out. So if you cut out like 40% and then you insert the image into this 40%, then you're just saying there is 40% of this image and 60% of that image. And you can, this is a computer does.
Okay.
You're just saying 40% of the pixels will be from this image. Then the label is 40% one image and 60% of the other image.
And the attentive cut mix is where you decide what's the important features.
Yeah, there is they use this attentive mechanism which knows where exactly the network used to look at the image to make a decision, and they specifically insert parts of the other image into these parts.
So that is it's algorithmically determined what's important. Okay.
Yeah. All right, so we can perform the augmentation, and the question might be, so when should I use augmentation? The problem is the augmentation is, the answer is very quickly everywhere you can, but the problem is not always you can use augmentation. Can you guys come up with a data set or type of data for which it is hard to do augmentation? So easy for images. Can you do augmentation for sounds? Can you come up with a way to do augmentation for sounds? For example, you have my voice. How can you augment a data set that would contain my lecture voice recordings?
Pitch it up and down, slow it.
Yeah. For example, you say just let's cut it into pieces and then just shuffle the pieces. And I have a shuffled lecture. If I want to predict if it's my lecture or Alexander's lecture, then you just, cut into many pieces, you shuffle them up, and then you just run the network on these. And you can do all sorts of cut mix type of augmentation on that as well. You can insert some parts of Alexander's lecture into my lecture, and then you can have all this kind of cool stuff, right? All right, what about text? Can you do augmentation with text? Let's say I want to predict if the comment under my lecture is positive or negative comment. So how can I augment this data set? Oleg, what do you think? Can you do it for text?
With, how it's called? Sentence.
You can.
You mean with text. You mean this emotion, yeah, that it's negative, positive?
Doesn't matter. Any kind of text. How can you augment text? Create more data from text.
Yeah, change places, of
so you can
sentences.
Shuffle the words, or you can shuffle sentences, but would it still be the same text? Would you kind of...
Yeah, it could be the problem, yeah. It could be the different than meaning here, if it shuffles the words or sentences.
I am married to the dog and I love my wife. You could switch those around and you have different sentences.
Yeah.
I think we can skip some words, so not important one.
The same question, which one would you skip? The dog, married, or wife? Right? So which... No, but well, just to help you a little bit. So there is not that trivial way to augment text. People came up with this brilliant idea of generative adversarial networks, GANs. So they can generate a lot of text by not just not GANs, because GANs usually used for images, but there are networks that are based on the same type that can generate text. So there are models that can generate text from the text space. So you give a corpus of text, and then it starts to generate similar type of text. But again, there is still kind of some fear left that this text that will be generated will not look as a genuine text. So it's not really easy to augment the textual data. Not as trivial as imaging data. Not as trivial as imaging data. There are ways, but it's not as trivial as imaging data. Kenneth, you were saying?
Put it through translation. Translate it English to Ukrainian, Ukrainian, French, French back to English.
Yeah, slightly, and then you get the gibberish back, right?
I mean, sometimes those things are not, they're not too far off, but yeah, I wouldn't trust it for anything. Yeah.
So that's the thing, right? You wouldn't trust it. I wouldn't trust it either. Why would we trust these kind of texts to the machine learning algorithms? But I'm just saying that texts are not so easy. But there is another type of data that is even harder. Something that is even harder. Any examples? Elena, Igor, what do you think, guys? Any examples of the data that could be even harder to augment than text?
Maybe some real data, for example, healthcare data.
Yeah, tabular data, right? Healthcare data, for example, blood pressure, or I don't know, blood count, whatever have you. How can you augment? Can you generate a random fake data? Does it make sense? Not sure. What if you generate too high blood pressure, too high blood count? Would that make sense? Is it useful? Nobody knows, right? There are still ways to do it, but they are even less trivial than with text. So I would say that tabular data is very hard to augment. But still, if you can do augmentation, you should do augmentation. In most of the cases, it helps. Yeah, so here I'm just saying that all data is easy to augment. So yeah, these are implicit and explicit regularization methods. Before we go on, I wanted to go back to my
to wrap up.
Yeah, sure, go ahead.
The regularization comes by just having large data sets. So
just having big data set is a good way to regularize your model.
So if you have an actual authentic super large data set, then regularization doesn't actually become an issue. Regularization is a problem of data sets.
Small data sets. Yeah. Okay. Yeah. It's usually a problem of large data sets or very, very powerful models. So you have very powerful model, then maybe even a large data set wouldn't be enough. And then you might still want to go for the L2 or L1 regularization. And yeah, so this is still possible. But let me go back to this, my collaboratory, and now my runtime, actually, I lost my runtime, which means that I need to rerun these cells. Sorry, I need to start from scratch with we shall use CFAR10 data set. I need to plot the...
Fix ACC needs to be changed to accuracy if you want to plot.
Accuracy, okay. Thank you. And this one as well, right?
File accuracy, yeah.
Okay, thank you. I was just about to check that. Thank you very much.
Mistake. Accuracy. You made a mistake in accuracy word.
Oh, thank you. Sorry for that.
Data augmentation.
What?
Data augmentation, I think.
Where is that?
Kind of data augmentation. I just say that
the text is a text augmentation. Got it. Thank you very much. I'll actually post it into Slack just to. Oh, thank you, Kenneth. Thank you. This is very useful. I'll post it here so that you guys can please copy the correct version, and also for Igor, I will post it into chat here as well, just so you guys to know that there is a mistake here.
Thank you. Not really needed. Well, I've just completed with my hands.
All right, thank you. I just made a. This is great. I just to make sure, So don't take it. Yeah, I just want to rerun these things to make sure that they run, so that you guys have you know, you don't have mistakes when you do homework. That would be awful. I'll just cut down the number of epochs to 10, just not to wait for half an hour. So you can see each one of my epochs is taking 11 seconds, so it shouldn't take too much time. The first epoch takes a bit more seconds. You know why? Why the first epoch takes usually more time than the other ones?
I have no idea why.
Because we started with some initial fake coefficients, yeah, whatever.
Yeah, but initialization happens here. What usually happens here is all this hardware setup. So you need to make sure that GPU works, and then you connect to your GPU and that kind of thing. So the hardware warm up happens on the first epoch, and that's why first epoch usually takes a bit more time than the other. And yeah, you can so you can check out the validation loss. You can see that my validation loss is getting down. My accuracy is increasing, so everything looks fine. I'm not sure if that is the way how it's going to be until the end. So validation loss is decreasing. Sometimes you have something that is called early stopping. Do you guys know what early stopping is?
Yeah.
So when the validation loss stops decreasing for some time, it basically it stops. So the training process is stopped if the validation loss stops decreasing. For example, you can see that I had 0.81 here, and now I have 85. If that trend would continue onwards for, like, let's say 5 iterations or 5 epochs or something like that. This is, by the way, tunable parameter. You can set the patience to anything you like, and then it would just stop the execution, stop the training. Oleg, why would you stop the training in that case? Why would you stop? If the validation loss does not improve, why would you stop?
If validation was it's not improved, then maybe we achieved our minimum, yeah. So
yeah, we are just we are having overfitting. We are having overfitting. So do we have overfitting right here?
Not really.
Not really. We don't really have overfitting here. But if we continue training, then maybe at some point you will see that there is some overfitting happening.
Okay, yeah.
We can evaluate the model and check what's the model performance. And the first one is the loss on validation on the test. On the test. And the second one is accuracy. So our accuracy is 76%. What would be the accuracy of the random classifier here? Igor, what would be the accuracy of the random classifier?
Random classifier.
50%.
How many classes do we have here? How many classes do we have?
10.
10.
01.
01, so that would be 10%, right? So the random classifier would be 10%, and we are having 76%. So we are much better than random classifier, which is pretty good. And in here, I'm actually, I propose you to go through and try to find lambda for which the performance would be better, right? So this is part of the homework exercise. I mean, you can run it as well. This would be basically, this would result in another 20 epochs, and then you can plot the curves and you can evaluate the model. And then in the exercise, I propose to implement the same cross-validation algorithm you will do for the previous homework, but now just looking for the lambda parameter. You can limit your model training to, let's say, several epochs. So not running 20 epochs, because otherwise it would take you a lot of time. So you can limit it to, let's say, 5 epochs or something like this. And for each of these lambdas and maybe more that you can, maybe you can add few or you can change some of these lambdas, find the lambda for which your model will perform better, visualize the your curves, plot your curves, and then evaluate your model on a test set. The last part of this practical is augmentation. So I again use the TensorFlow version 1.
Sorry, where can we see in this code execution traceability between batches and epochs? So
there is
so
none.
now I'm
none.
confused.
So each point in here is the average across all batches.
One epoch.
Average.
Yeah, so you take all the batches that you have, right? You compute the training loss and validation loss for each batch, and then for all training you take the average. So this is the average.
Average for so first we calculate training loss. Again, for every batch we have average value, yeah, of every batch.
No, we have average value for the entire epoch.
Epoch.
Yeah. So we calculate. We calculate average loss per batch for. So what is the loss of the batch, and then we calculate all the losses of each batch, and then we take the average, right? And that would be 1 point on this graph. So this point here of the first epoch. Okay, I'm showing validation. Okay, training. So the training here has loss of about 1.6, or actually 1.5. So 1.5 on the first epoch means the average across all the batches of the training data.
And this batch size limits our resources, like computation resources, yeah, that we cannot put all images to one batch, let's say.
Yeah, this is a very interesting question, because if you think about this, how many times you would need to run a backpropagation algorithm if your batch size would be half of your data set? Igor, how many times would you need to run backpropagation algorithm if your batch size would be half of your data set?
2 times.
2 times. So you would run it once for one batch and the other time for the other batch. If you make your batch size very small, then basically you will calculate backpropagation more often. But at the same time, you would also need to store less images, less weights of the network into memory. When you do a backpropagation algorithm, you would need to remember what were the outputs and inputs of neurons. Remember, we calculated backpropagation together. We needed to remember these outputs and inputs of each neuron. So for each image, these are different. So you would need to keep all these in memory. When you have a large batch size, then you would need to keep more of these inputs and outputs of each neuron in the memory.
Okay, so then what's the rule of thumb here? So what?
I think the rule of thumb usually is that make as large batches as it fits into your memory, because it would usually result in less backpropagations. Usually it results in the faster training. And if
so
you have a good GPU
between memory usage and computation resource
and
usage,
speed, and speed.
Okay.
So on the loss and accuracy on test set line, so X test, norm, Y test, so those two numbers. So explain to me the differences between those.
So this is a loss.
Yeah.
And this is the accuracy.
Okay.
So 76%, that's what we're getting. And this is the loss, which is a sparse categorical cross entropy of the entire test set.
All the loss.
Of the entire test set. All right. Any questions? Any more questions about this? More questions?
Yeah. So I mean, so just while you were speaking, I did the L2 regularization.
Okay.
And ended up with loss and accuracy, the 0.80 and then 0.78. So an increase in the first number, but not in the second number. And so I'm not sure entirely how, how to interpret that. It seems like the L2 propagation did not help.
Yes.
Yeah, this is possible. So you were saying that one of the numbers increased and the other one decreased, or which one?
So it went from those numbers to 0.80 and then 0.78. So a large
0.78 here,
yeah,
and 0.80 here.
Yeah.
So how it can happen that you may have higher accuracy but higher loss, right?
Yeah.
So you have bigger error but still higher accuracy. How this can happen? Anybody can speculate? Why would you have higher accuracy but at the same time higher loss? Simon, what do you think? Why would anybody have higher accuracy but at the same time having higher loss? Any idea?
Black magic.
Black magic. So the thing is, sorry, Igor, you had some?
No. Okay.
Lena, did you have also some ideas? Okay.
Here we speak about total average, sum of average, error, total error. It is not
Total
average
error.
error. Total error, okay.
No, this is,
So-
no, wait. This is average for test images. Yeah, this is average. This is average across the whole test set. This is not a sum. This is total, this is average across.
So
all tests.
divided by n.
Divided by n, yes.
So we have balanced set data set.
This is a very good question. This is like a super important question.
Because I have no intuition on how to evaluate whether I've improved things by adding the L2, because I've increased both sides of the equation, the loss by more, but
okay, okay, let me ask you this question. What do you care in the test set? Do you care about the number of images that you predicted correctly, or do you care about the score, the score distribution of scores per image was closer to perfect?
And fundamentally, accuracy, the larger purpose of the whole event, thing is accuracy.
Yeah. But how the loss can increase? So let me tell you this: when do we choose how to? So when we decide on the class for image, how do we choose which class it is the image of? What is the class of the image?
Threshold 50%, less than 50%.
Yeah. So basically, what about multi-class classification? What if we have 10 classes here?
The highest probability.
The highest score, right? So we predict the score for each class, and then we take the one that has the highest, and we call it this one.
Yeah.
That is the correct one. So why could it happen that we increase the loss, but also we increase the accuracy? It means that it's just it was enough score to call that class correct. I mean, the call to classify that image into the correct class, but at the same time, the distribution of score, the way how we distribute the score wasn't really good, right? But it was enough to predict the correct class.
Yeah. Okay.
So
I can. So go ahead, Simon.
So let's imagine this kind of case when you have cats and dogs, right?
Yeah.
You predict the class correctly. So this is 51% to the class cat. This is correct class, and then 49 to dog. I mean, I guess maybe in the case of binary classification, this will not work. I need to write it up. Not sure if this would work, but okay, yeah, this would work. So imagine it like this. So we have 5 images, four of them cats and one of them is dog, right? What happens is in the first case, we predict first 2 images perfectly. So 100% cat. And the other images we misclassify. So we are not predicting them correctly. So the class doc is higher, and so we misclassify these. But in the other case, we predict the scores just barely enough to classify 4 images correctly, but the class scores are not as perfect as in the first case, right?
Yeah.
For the first 2 examples. So this overweights the accuracy.
Yeah. So I mean, in some way, it's like you're less certain about it, but you're more right.
Yeah, you're more right. When you draw a line somewhere, you're more right, but at the same time, you're less certain about it.
Yeah, okay.
That's a very good intuition. Less certain about it, but you're right. Whew, okay. More questions? Because I want to show you augmentation before we stop. So we use this CIFAR 10 again. So we load the CIFAR 10. We generate something called data generator. The image data generator is the framework that is used to apply a series of transformations to the input images. And this is an example of very simple pipeline, a very simple image generator pipeline. So what it does, it rotates randomly images to a degree from 0 to 9 degrees. And randomly, it chooses randomly. I don't remember exactly how many images, but I think there's something like a third. So it's like 0.33 probability that you would rotate the image from 0 to 90 degrees. And the degree is also chosen randomly, okay? You also shift images horizontally by a fraction of the width of the image from 0 to 10%, right? So you can shift the image horizontally, meaning to the left or the right, by as much as up to 10% of the image width, right? You can do the same thing with a vertical shift. And again, this is all done for the random 33% of the data, right? So 1/3 of the data. And also you do horizontal flip also in this 30% of the cases. Right. So each one of them is for the random 30% of the cases. You may have for one image you may rotate it with the probability 30%. You may also shift it horizontally. You may also shift it vertically, and you may also flip it again with the probability 30%. It can happen that for one image you can have all 4, and it can also happen that for one image you may not have any one of them.
And so the idea of this is that, I mean, for me as a human being, I look at these pictures and I say, oh, that's just that picture, just shifted a little bit. From the point of view of the model, it's a completely different picture. There's no...
I wouldn't say it's a completely different, but it's quite different. Yes, it's quite different. Yeah. So it's almost like a new image. So when we run this and we feed it to the X-train here, we now can visualize. So this is how you work with this data generator. You use a datagen.flow, meaning that you feed in some images, and then you say, hey, give me the augmented images back. And you can extract these batches as many as you want, right? So you can extract the batches as many as you want. And these are the augmented images. You can see that they are churned. For example, you can see some empty corners here. You can see that a lot of them actually turned. Some of them are probably flipped as well. They're vertically shifted. So you can see this pattern here. This is a frog, obviously. And this pattern here means that it just copied the parts of the image just to fill in the parts. Now we can, I don't think I have recorded these. I just visualized them. I split my data into train and validation. And this is very important. The data generators in Keras do not have validation split that we used before. So we cannot really say use 10% of my data as validation because there might be a problem. What could be the problem, ladies and gentlemen? What could be the trouble? When you split augmented data into validation and training data, what could be a problem? Anybody? So I take my I take my data set, I augment it. So now for each image I have like turned versions, rotated versions, some kind of, I don't know, added color or whatever, and then I split it randomly into train and validation set. What could be a problem?
The problems that, let's say, then we cannot trust this validation set anymore, yeah?
Exactly, we cannot trust the validation set. This is related to the question that Kenneth asked before, right? He was asking whether, let's say, this image that is rotated is exactly different image, is very different image from the original image. Not exactly. So for a model that knows that this image is a truck, then predicting that this the original image is truck would be much simpler. So when you divide your augmented data into train and validation, when you use validation set that contains some images that you had in the train set, you basically will you will overfit. Your validation set will not be trustworthy.
So you should split it before you do the augmentation.
Exactly, and that's what we do here. That's what we do. We split it before we do the augmentation. We normalize both parts. We normalize with the mean and standard deviation of the train data. We normalize the train. We normalize the validation. We normalize the test. This is what you usually do. And here we augment. So here we augment. I think I'll just copy it over. I think there's nothing really to copy over. I decided not to have any additional exercises here. So I apply a very similar pipeline that we had up there to the normalized training data, not to validation, not to test data, but to train data. Now I define a model which has some very small lambda. I use sparse categorical entropy and that kind of stuff. All is the same besides the model.feed part. So now it's a not model.feed, that model.feed generator, which uses a data generator flow. So it uses original my training data, but it also, it basically gets it through the pipeline of the image data generator. So it randomly generates augmented images. When we generate a new batch of size 64, this is an augmented batch of size 64, okay? This is an augmented. And this is where it makes sense to say how many steps I would like to take, because I can take as many steps as I like, because I can generate forever. I can generate data forever. It will not be as useful at some point because, well, I will basically generate all the same data again and again and again, but I can generate it many, many, many times. So that's why I calculate number of steps myself. In here, I just use the same number of steps as we would have without data augmentation, but you can definitely increase this number. And this is how I run it. This is how I run it. And yeah, so you should be able to see the history, and hopefully this will perform better. It's not guaranteed to perform better because, well, it's not always makes sense to rotate the deer by 90 degrees and hope that this is useful augmentation strategy. So you can change the augmentation strategy so that it actually fits your data, right? So it makes sense for your data. Do you guys have questions about this?
So my question is why you wouldn't increase the number of steps? If the point of the augmentation is to get more data, then why have the same number of steps, a smaller number of steps? Exactly.
So I did it just because I didn't want to wait too much.
Okay.
But you definitely, when actually this is the main point of the augmentation is to increase the number of data. So that's why you need to increase the number of steps comparing to what you would have if you would have no augmentation whatsoever. So this is a good point. So this number should be bigger than what you usually would have in the case of no augmentation. Anybody else? Any other questions? I want to ask for something. So these are the two exercises here that I want you guys to do at home. But so before we continue, there is something else that I have prepared. But since we had to go into deep learning part, I don't have much time for it. So it's a completely voluntary practice. So do you guys want to have a quick Kahoot? Do you know what Kahoot is?
No.
It's an interactive quiz. It's an interactive quiz. It will take us about 15 minutes or about that.
Yeah, sure.
I'm happy to stay up and just have the quiz with you guys because I prepared it and I think it's fun. I really hope that you can do it. Let's do it. How about doing it? I mean, if you need to go, you need to go. No problem with that. Yeah, let's have a vote. So who is for Kahoot? Who's up for Kahoot? Okay, good. Igor, how about you? Okay, great. Elena, are you still alive there? Just make it clear. Yay. Oh, she said something. You guys, she said something. Alexander, how are you? Okay, let's do it then. Let me share.
Threshold was very low. It was just you had to be alive. That's all.
Yeah, my bar is very, very low. All right, so let me do this. So I create my Kahoot. So what you guys need to do, you need to wait a sec. So there is one annoying feature of Kahoot is I have a music on and I can't switch it off. So what you need to do is you need to go to kahoot.it and I'll send it to Slack and to chat so that you know where it is. And just let me copy also pin here. Igor, I will just copy to chat. So if you go to kahoot.it, www.kahoot.it, we have Oleg and Kenneth, you were there.
Yeah, I just got kicked out for some reason.
Okay, Igor is here. Swift, Ibex 4, and Kenneth.
This is Semyon. I don't know why it gives me such a.
Okay. Yeah, Olena, everybody's here. Great. Let's then get started. So let's see how it looks. So there will be a question. Let's go. Quiz. Regularization in general is best described as, and you have to choose one answer out of 4. And you need just on your phone or your computer, you just have to click on the color box, right? The color of the box that you think is having the right answer. So is it preferring simple solutions over complex to avoid overfitting? This is one of the intricate feature selection techniques. This is a way to make a model weight small. This is selecting the best possible model over a set of all possible choices. So what do you think regularization in general best described as? 3 answers. We have 6 participants. 4 answers. 2 more people to come. So what do you think regularization in general is best described as? A way to make a model weight small. This is one of the intricate feature selection techniques. Maybe selecting best possible model over a choice, or preferring simple solutions over complex to avoid overfitting. Okay, the last answer, no pressure, but you have 10 seconds, 9, 8.
I made mistake.
That's fine. Don't worry about this. That's okay. So the correct answer was preferring simple solutions over complex to avoid overfitting. So selecting the best possible model over a set of possible choices is basically hyperparameter tuning, or cross-validation algorithm also fits into this description, but regularization is probably better described by red stuff. So here's the leaderboard. Kenneth is first, Oleg is second, Olena is third. All right, that's nice. Which of the following methods can be used for feature selection? Right. Tikhonov regularization, rich regression, lasso regression, or dropout. Which one can be used as a feature selection? Rich regression, lasso regression, dropout, or Tikhonov regularization? So what is that? What is that?
Strange.
Two more.
Strange that doesn't show answers on screen.
Yeah, you need to look into my one. So yeah, everybody was correct. So that's true. That's true. Lasso regression. That's a feature selection method. So let's see what's the leaderboard. Kenneth is still on top. Oleg is still on the second place. Olena on the third place. We have some Swift Ibex44 joining the top 5. That's pretty cool. True or false? Early stopping, interrupting training after several fruitless iterations, is an implicit regularization. Is it true or false? And remember, what is implicit regularization? What is explicit regularization? So when you limit your model creative capacity and when you give it more space. So what is it? Is it limiting capacity or is it giving it more space?
Berlum.
Limiting or giving more space? So 3 answers so far, 4 answers. It's 50-50, guys. Accuracy is 50% of the random classifier here. Just 2 classes. Toss a coin. One last person. And it is 50-50. Yay. Okay. So what did I mean by that? So early stopping, in my terms, is an explicit regularization because it limits the creative capacity of the model. So implicit regularization is the augmentation, for example. This is an implicit regularization. This is a good example of the implicit regularization. While early stopping seems like limiting the model, like it's limiting the model. So I would take it into explicit regularization method family, and that's why it's false. But I completely understand people who miss that. I would probably miss that too because it's fairly arbitrary. But anyway, all right. So we have Oleg, and
Oleg,
we have
Alexander.
Yeah, I guess. So Oleg just said that Oleg is not Oleg. Okay, but Olena is on the strike, ladies and gentlemen. She's on the strike. That's the 3rd answer in the row, correct. So this is pretty
So
impressive.
it seems like it also takes into account the time, yeah?
Yeah, it does take into account the time. So Tikhonov regularization is another name for data augmentation technique of rotating images. L1 regularization was linear regression. Reach regression. Linear regression was without regularization.
Oh, I did it wrong. You can't change your answer. It's super annoying.
You can't change it. I'm sorry. I had done it many times. We used to run these Kahoots in my team in the project, and then I would click on something wrong, and I would be like, "God damn it, I missed that." Yeah. So 4 answers, 2 more. By the way, this is a Moscow State University wall. So this is where Tikhonov Andrei Nikolaevich worked. 2 more answers. Ladies and gentlemen, no pressure, but Kahoot takes into account time. So the later you reply, the lower number of points you get. Sorry for that.
Yeah, no, you are causing pressure. I pressed the wrong color just by excitedly clicking before my mouse got there. So
I'm sorry.
So you're wrong if you think there's no pressure. There's a lot of pressure.
Oh yeah, gotcha. Yeah, so it's a ridge regression. So L1 regularization with linear regression is lasso, right? So it's that is true. Okay.
I was trying for 900 points there.
I was okay. So now Alexander came here, and he's just wrapping up the leaderboard. So that's let's win it, ladies and gentlemen. I encourage you to win. ElasticNet is a combination of L1, L2 regularization and linear regression, a neural net which generalizes well to unseen data, another name for ridge regression, or way of making linear regression very elastic.
It's
5
more
answers.
important to to be fast.
What were you saying?
Yep, fast is the secret.
Yeah, fast is the secret.
Okay, let's see if you guys did it before, Alexander.
No.
Not really. Not really.
Oh, I'm not even in the top 5 anymore. This is terrible.
Don't worry about this. You'll have time to catch up. Okay, so there are still questions to go. In mini batch stochastic gradient descent, dropout is not applied at all, applied to every batch separately, applied to every input data point separately, applied to random input data point.
I don't remember this at all, mini batch.
It doesn't matter, just stochastic gradient descent. Think about back propagation. I mean, in the feed forward case, in the case of feed forward, it doesn't matter. Feed forward is part of the mini batch stochastic gradient descent. Mini batch stochastic gradient descent is when you take a mini batch and you put it through and you calculate the feed forward and then back propagation. This is what's called mini batch stochastic gradient descent. Okay. Nothing really fancy here. It's all the same humdrum gradient descent calculation.
Yeah, it's really a question about dropout.
Yeah, it's applied to every input data point separately. That's what we discussed during the lecture. It's not about batch, so not to every batch, but actually to every data point. I'm wondering what do you think about not applied at all? Of course, it's applied. It's applied to the network architecture. Yeah. All right. So let's see how the Alexander.
We can start.
When performing backpropagation step for WI, L1 regularization becomes. That's a complicated one, right? So you remember we talked about weight decay. What does L1 regularization term, which is this guy here, what it turns out to be when we apply it in the backpropagation case? We have to take a gradient with respect to WI.
Oh my God.
Oh my God. Yeah, can we somehow maybe blindfolded Alexander's just for a few questions and then? Oh, that's nice. You guys remember it. That's so cool. I was afraid that nobody will remember that. So when you take then take a derivative, you obviously get rid of WI, so you're left with just lambda, which is the right answer. Oh, Kenneth, welcome back to the top 3. Actually, top 2, right? So that's pretty good. Which of the following statements is true? Which of the following is true? Weight decay is L1 or L2 regularization applied to neural networks. L1 regularization is the same as lasso, and L2 is the same as ridge. And L1 regularization is the sum of weights minus intercept. L1 regularization plus linear regression is a ridge regression. So which one is true? We already have 3 answers. I'm pretty sure Alexander has already voted. You guys should catch up.
Oh, fuck.
4 answers.
Selected wrong. Okay.
5.
Right.
Yay.
Yeah. Shit.
Weight decay is the L1, L2 regularization applied to neural networks. So L1 regularization is not the same as lasso because L1 regularization is L1 regularization. Lasso is a linear regression plus L1 regularization. L2 is not the same as ridge because L2 plus linear regression is a ridge regression. Okay. L1 is not a sum of weights minus intercept. It's basically just sum of weights. No, intercept is not taken into account. L1 regularization plus linear regression is lasso regularization. Okay. Kenneth has done it. Nice. And Oleg has done it as well. By increasing the value of lambda in L1, L2 regularization, weights of the resulting model get useless, get bigger, get smaller, don't change. So what happens to the weights of the resulting model when you apply L1, L2 regularization? They get useless, get bigger, get smaller. They don't change. Okay, the last one. Yay, congratulations. Everybody nailed it. Yeah, that was okay. Oleg, Oleg, I mean Alexander, I hope that you wouldn't be fine if I would say that Kenneth is the first place person here. I'll take you to another class. All right. So we have a top 3: Kenneth, Olena, and Oleg. Okay. What has that saying? No, I don't wanna exit the game. Why is
No way.
It is recommended to split data into train and validation before the augmentation? Why is it recommended to split before we do augmentation? Otherwise, the test error won't be meaningful. Otherwise, the performance of the model will degrade. Otherwise, the validation error won't be meaningful. And otherwise, the validation set will grow too large. All right, so what is it? Why is it recommended to split before the augmentation, not after the augmentation? Three answers so far. The time is ticking. The time is ticking.
Time is scorers.
5. And the last one. Yes, the blue one is about, no, the performance will not degrade. It's just the generalization power will degrade, not the performance, not necessarily performance will degrade. It's just the validation error won't be useful because it wouldn't represent the real state of things. So it wouldn't be useful. Okay. The Oleg is still on top, but Oleg went into the second place of our internal top 3. Kenneth remains leader. Yeah, it's pretty cool. The last question has double points.
Wow.
Double number of points. No free lunch theorem for machine learning states that no machine learning algorithm can be fully trusted. No machine learning algorithm should be used on unseen data. Universally good machine learning algorithm is hard to design and implement. And no machine learning algorithm is better than any other across all possible data sets.
Wow.
I know that you don't know what the free lunch theorem says. And that makes it even funnier. Try to guess, because it has this free lunch kind of thingy in the name. And you have this mousetrap here in the picture. What that could possibly be about. What it could possibly be about. Why did I choose this question is that there are many, you will hear it many times, people saying no free lunch theory in machine learning. And it's kind of nice if you could, you know, if you can just say, I know what no free lunch theorem actually is saying. Okay. So no machine algorithm, no ML algorithm is better than any other across possible data sets. That's the true answer. What does it mean? Can anybody tell me what does it actually mean?
Well, an algorithm is designed to solve a specific problem of a data set, and a different data set has different problems. And yeah, basically, no, it doesn't matter how deep is your network or how intricate is your model, it will not perform better than random choice in some other data set. You can basically end up having the same performance as a coin flip in some other data set, okay? And across all these data sets, it doesn't really matter which one you choose. But as Kenneth is saying, of course, we are not designing an algorithm that would work for all problems. This is what machine learning, this is what no free lunch theorem in machine learning prohibits, is this kind of universal, absolutely universal algorithm that would work for all possible circumstances. That's why this is what machine learning no free lunch theorem says. So I have a question.
Wait. This is important. Oleg is the third place. Kenneth is the second place, and we have
Oleg again.
Yay. And we have runner-ups, Igor and Olena. So I'll just make a picture of this and I will close it. Yeah, sorry. Kenneth, you were saying.
Yeah, actually, something that kind of crossed my mind the other day was that with so much changing because of COVID-19, is everybody's machine learning models about consumer preference and economic behavior and traffic and the spacing of subway cars, is all of that going to have to be thrown out because the data sets won't apply anymore because people were going to be acting differently?
Well, if they would be acting significantly differently, then possibly in some areas, of course, this could cause trouble for machine learning. I mean, even
if I was in charge of all the machine learning that's doing pricing for airlines or pricing for hotels, I mean, that's different. That's not going to be the same anymore.
You would definitely, you would be suspicious. You would definitely do something about it. Yeah. So there is a concept in machine learning called domain shift. All right. So this is when exactly what you were saying. For example, before COVID, prices on the airline travel, and then after COVID, prices will change. And this is basically what people in machine learning call a domain shift. So the models that were trained on the old data sets will not work as well for the new data. And this is what is called domain shift. And domain shift is one of the implications of the no free lunch theorem. And they could be large and they could be smaller, right? So sometimes you take another camera. For example, you were taking pictures with your Samsung S10, and then you took, let's say, 100 pictures, and you trained your model on these pictures, and then you took your iPhone and you went outside and you made another 100 pictures. So your iPhone pictures may not do as good job your model will not do as good job for these iPhone pictures now. And this is maybe a minor domain shift. While if you take, let's say, instead of your Samsung S, you take a microscope and you start taking microscope images, then this will not work at all, right? And then your model will perform not better than random guess. Any other questions? Anything else that you wanted to point out? Otherwise, I think we have done enough for today. So the homework is due June 4. So this is the deadline for this homework. Let's discuss things in Slack. The next time we meet, we do ensemble learning. There will be 2 parts of the lecture about ensemble learning, and the final will be about time series. Okay, and we will have 2 more homeworks from each one of the parts about ensemble learning and one about time series.
And when is that? When is our next meeting?
The next meeting is 29th of May, in 2 weeks' time.
There you go. Yeah. Okay.
Okay. Any questions before we call it a day? Yeah, let's cut it out. Thank you very much, guys, for being here, and thank you for Alexander for joining as well. And hopefully, I can't see Elena is not around. Okay. So no, Elena is around. Elena, I'm glad that you also found power and energy to stay up and be with us. So thank you very much, guys, and see you on in May 29, right? So this will be the next meeting. Okay, bye-bye. Let's keep in touch in Slack.
Thank you. Bye-bye.
Bye.
Bye.